Okay, next learning goal. More definitions, this time some equations, and specifically for internal energy. And we're going to set up the definition for the first law. So let's see, find a slide. So there we go. Internal energy, as we noted, gets a capital letter U, indicating that this is a state function. So internal energy, we really think of as the total energy. So it is the kinetic plus the potential energy of the system. So when we talk about this in terms of the delta, we're often referring, let's try that again. Let's erase that. So recall the delta, that refers to measurable changes. So what we might be able to achieve in the laboratory. Whereas du, right, that gets into our calculus, our infinitesimally small changes that we're going to use to work out fundamental relationships. So the unit for total internal energy is the joule. And expressed in this way, this is an extensive parameter. So the more that we have, the more mass, for example, that we have, the more total internal energy that we'll have. We're going to often see the intensive form of this used, the molar internal energy, molar internal energy. And when we see that little m right there, that means U divided by N, just like what we saw with volume in gases, the molar volume. And so, right, that is two extensive properties, right? We know moles would be an extensive property. We know energy is an extensive property. So two extensive properties divided by each other gives us an intensive property. So one that does not matter of the amount. So this would obviously give us joules per mole, but more often we're going to see this expressed in kilojoules per mole. Okay. So moving on, as we're going to discuss a lot in this semester, which is why we had our crash course in STEP-MEC, I'm often going to refer to the molecular versus the bulk. And what I mean by that is when we look at our bulk properties, like heat capacity, density, and so forth, I'll often refer to these as our physical observables. So things that we can actually measure. These are all stemming from those molecular properties. Things like its structure, so its ability to vibrate or rotate, etc. Things that we might have a harder time observing. So those properties are directly observable through the bulk properties. So let's define thermal motion. So that's the disorderly motion of molecules specifically resulting from heat transfer. And here I put this question, exo versus endo. So recall from our discussion of STEP-MEC that energy is stored in the molecular modes. So when we talk about an exothermic process, heat being given away, heat is given away, it's coming from those molecular modes, right? So it is going to go from the molecular modes out into the surroundings. However, with the endo, right, heat is being absorbed, and it is being absorbed specifically by those molecular modes of motion, okay? So recall we discussed the degrees of freedom in our introduction, right? We get our 1/2, and I'll write it as RT because we've got the molar internal energy. We get 1/2 RT degrees of freedom for a simple atom, giving us a total internal energy of 3/2 RT. It's important to note, right, we talked about this as both the potential and the kinetic, but recall in an ideal gas, there is no interaction. So really, I'm going to say kinetic only for ideal gases, okay? So that is to say the ideal gases, we don't consider their potential energy because the potential energy doesn't matter. As it turns out for real gases, or I should say kinetic only for real gases. Let me write that down, apologies. Kinetic only for real gases, right? Because in real gases, there is a potential energy that we have to consider. This is only considering the kinetic from their thermal degrees of freedom. And for a simple atom like this, there's only these 3 degrees of freedom, okay? Just to play on this delta just a little bit further, if we consider this occurring at 2 different temperatures, so for example, UM at T final minus UM at T initial, and that still equals 3/2 RT. If we set our stage all the way to 0 Kelvin, then and approximating that energy will be 0 at 0 Kelvin, then we can just write that the molar internal energy without the delta as a function of temperature is simply 3/2 RT, right? So if we relate that all the way down to 0 Kelvin, we can get rid of the delta, right? So now, what about these 3 degrees of freedom, and what can we say about more complicated molecules? Well, as it turns out, there are additional degrees of freedom for the rotations. The vibrations just simply don't have enough population of states to make a difference here. So we're going to count up the 3 degrees of freedom from the travel, from the motion in XYZ. And we have to look at the degrees of freedom for rotations. So we're going to put this in different classes. So our first class here was just a regular old atom. So now here, this is an example of CO2. So this would be a representative linear molecule. And now we can see here there's 2 rotational degrees of freedom, right? It can rotate about the XY, or it can rotate about the YZ. So what that means is we get 2 extra degrees of freedom on top of the already 3 that were there. So that makes 5 degrees of freedom. So that means my molar internal energy for a representative linear molecule is 5/2 RT. Okay. And recall, for a simple atom, it's just 3/2 RT. So now what about a representative non-linear molecule? So, and this, hopefully you can tell, is a picture of water. So we can get to a non-linear molecule by recognizing that it will have 3 unique degrees of rotational freedom. So that means in total, it's going to have 6 degrees of freedom, 3 translational, 3 rotational. So that means my molar internal energy for a representative nonlinear gas is 6/2 RT, or just 3 RT. So we can see there is a difference in the molar internal energy depending on what the structure of the molecule is. And again, that's because the molecular modes store energy. And then finally, the last thing to unpack here, and we'll spend most of the semester unpacking this, just a brief introduction for now, the first law. Okay, so there's a couple different ways we can state the first law. One is the internal energy of an isolated system is constant, and I'll underline that word. That's important for the statement. Another way we can state this, which is probably more practical for the way we apply it, energy cannot be created nor destroyed, but can be converted from one form to another. So mathematically speaking, that gives us these equations right here that says the change in internal energy, so, right, change in, I'm going to write IE for internal energy, is equal to work plus heat. So we can exchange work and heat in terms of the internal energy as long as we haven't created any new internal energy, right? We'll also note here, once again, by using the delta, this is measurable, what we would typically see in the lab. And this du, infinitesimally small changes. Infinitesimally small changes. So this is how we're going to work out relationships, equations, proofs, etc. Okay? So we need to be comfortable with using both and how to interrelate them. And we should recognize, as long as we have a state function, then the final product of those is one and the same. But for our path functions, right, like w and dw, those aren't necessarily the same depending on the path that we take. And we're going to explore more about those paths in the coming videos, so the types of work and the types of heat that we can use. Okay, folks, I'll see you in the next one.